When you hear the term large language model, your mind probably jumps straight to chatbots, right? But what if I told you that conversation isn't even their coolest trick? Their real superpower is something else entirely. Today, we're going to dive into how these models are, quite literally, the most powerful knowledge compressors ever created. So, let me start with a puzzle for you. Imagine you have an entire library, all those books, all that history, all that knowledge. How in the world would you cram all of that onto a single hard drive? I know, it sounds like a trick question, maybe even impossible. But trust me, the answer is the secret sauce to understanding what makes these models so powerful. To crack this puzzle, we've got to look at two totally different ways of storing information. On one side, you have your classic database. Think of it like a giant, super organized address book. If you need a specific piece of info, you just look it up. It's right there, explicit. We call that non-parametric knowledge. But then, you have an LLM. And an LLM is way more like a human brain. It's not just a big list of facts, no way. It learns the connections, the relationships between ideas. And that is parametric knowledge. It's all compressed and woven right into the fabric of the model itself. So, the big question is, how do you actually build one of these? These knowledge brains? Well, it turns out there's a pretty specific blueprint. And if we walk through it, you'll see exactly how this incredible compression actually happens. It really all boils down to a three-step recipe. First up is pretraining, which is where the model just learns about the world. Then comes supervised fine-tuning, or SFT, where we teach it to follow instructions. And the final polish is reinforcement learning from human feedback, RLHF for short, where it learns to be genuinely helpful and safe. So let's take a quick look at each one. Okay, so that first step, pre-training. Let me tell you, this is the heavy lifting part. This is where the model basically ingests a huge chunk of the internet, tons of books, articles, you name it. But here's the crucial part. It's not just memorizing stuff. That's not the goal. Instead, it's learning the deep underlying patterns of language, grammar, context, how ideas link together. Its entire job at this stage is to get insanely good at one thing, predicting the very next word in a sentence, and through that simple task, it builds this massive foundational understanding of the world. So after all that pre-training, you've got this model that's like a genius who's read every book but doesn't know how to have a conversation. It understands language, but it doesn't know what to do with it. That's where supervised fine-tuning steps in. We basically show it a bunch of high-quality examples, like here's a question and here's a really good answer. It's kind of like sending the model to finishing school to become a helpful assistant. It's what turns it from just a next word predictor into something that can actually answer your questions. And now for the last step, which honestly might be the most important piece for making these things actually usable. With RLHF, we have actual people, human trainers, who look at the model's answers and rank them. They'll say, yep, this one's great, or nah, this one missed the mark. Then a separate reward model learns from all those rankings. It figures out what we think makes a good answer. Is it helpful? Is it safe? Is it truthful? This whole process is what aligns the AI with human values. It's the final, crucial polish. Okay, so now that we've seen the blueprint for building an LLM, let's circle back to where we started, this idea of compressed versus indexed knowledge. Because it turns out this whole three-step process creates this really fascinating trade-off. A trade-off between how tightly you can pack information and how fast you can get it back out. And this is where it gets really interesting. Just look at the numbers. On the storage side, an LLM crams all its knowledge into, say, a few hundred gigs. But a comparable database doing something similar, that could easily be terabytes of data. So the LLM is way smaller. But now, look at the speed. The database is ridiculously fast. We're talking 50 milliseconds to find something. The LLM, on the other hand, has to think. It has to generate its answer from scratch, which takes a lot longer. So you see the trade-off, right? This is the key. An LLM makes a very specific choice. It gives up that lightning-fast retrieval speed. And I mean, we're still talking about fractions of a second here, in exchange for an absolutely insane level of information density. It's not trying to be a super fast search indexed. It's trying to be a deeply compressed archive of human knowledge. I know this all might still sound a little theoretical, a bit abstract, so let's make it super concrete. Let's look at a real-world example that is just, well, it's mind-blowing. We're going to check out a model called Kimi K2, and you'll see just how far this knowledge compression can actually go. All right, so where does it start? With the raw data, of course. For the Kimi K2 model, the starting point was a mind-boggling 15.5 trillion tokens. Now, a token is basically a word or sometimes just part of a word. 15.5 trillion of them. It's a number that's just hard to even wrap your head around.
So, what does that actually mean in terms of file size? Well, 15.5 trillion tokens works out to be about 62 terabytes of raw text data. To put that in perspective, that's like having a stack of dozens of high-capacity hard drives, and every single one is just jam-packed with pure information. Okay, so we have 62 terabytes of raw material. Then we put it through the entire process, the pre-training, the fine-tuning, the human feedback, the whole shebang. And after all of that, what's the size of the final model? Get this, just 1 terabyte. And there it is. That's the punchline. You start with 62 terabytes of source material, and you end up with a 1 terabyte model. That is a knowledge compression ratio of 62 to 1. Think about that. All the essential knowledge, all the patterns, and the deep relationships from that massive library of data have been distilled down into something that can fit on a single drive. And that word distilled is so important. This isn't like zipping a file. You can't just unzip the model and get the original 62 terabytes back. No, this is something different. The model has created a whole new representation of that knowledge. It's extracted the very essence of it, all those statistical connections and underlying concepts, and it's encoded that essence into its network of parameters. So what's the big deal? Why does any of this matter? Well, this is way more than just a neat tech trick. This kind of compression, it's a totally new way of thinking about, storing, and even interacting with knowledge. And honestly, the implications for our future are massive. So let's recap the main points here. First, and most importantly, LLMs are not databases. They're incredibly efficient knowledge compressors. Second, they do more than just store facts. They learn the relationships between facts, which is what lets them come up with novel ideas. Third, this crazy compression means we can start putting huge amounts of information on our own local devices. And finally, the price we pay for all this density is just a little bit of speed. And all of this leads to one last, kind of mind-bending thought to leave you with. Right now, today, we're seeing compression ratios like 62 to 1. But what happens when that number gets to 100 to 1 or even 1,000 to 1? What new possibilities open up when we can genuinely distill the essence of the entire internet onto a device that you can just carry around in your pocket? I mean, that's the question that's really going to shape what comes next.